Okay, welcome to related rates. Okay, tricky part, tricky definitely, and this is just it's related rates is all about one thing is changing, and it's affecting the rate at which something else changes. So if a car, if its velocity changes, its gas mileage might change too. That sort of thing. But in this case, we have how fast will the water level inside a cylinder tank drop if the water is drained at 2,800 liters per minute. Okay, so we have a tank here, and we're going to drain some water out of it. We have a little valve here that's engineered to let water out at the rate of looks like negative 2,800 liters per minute, and it's negative because water is leaving the tank. So that is the rate at which the volume changes over time. So we can actually call that the derivative of volume with respect to time. Okay, so that was basically given to us right here, that the water is drained at 2,800 liters per minute. So that's the rate at which volume changes over time. Okay, R, this is the radius. And as the water drains, the radius is going to stay the same, so it's going to be constant. I left it as an R on purpose because sometimes it's a little tricky. You want to treat it like you're used to treating it like a variable, but we're going to treat it like a constant this time. And then we also have H, the height. Okay, and go back to your volume of a cylinder is pi r squared h, but this one is 1,000 pi r squared h. Okay, so volume is changing and the height is changing, and they're both changing at different rates. Okay, and we're going to figure out both of them because they gave us this one rate. And our goal is going to solve for this rate. So let's go ahead and do that. Okay, I'm going to get another piece of paper and I'm going to write down everything we know. And notice I already drew the picture, but always draw a picture. I drew a really big picture. It's real big, and you don't have to draw. It doesn't have to be neat and accurate. Notice how this isn't a real right cylinder. It's not. But it gets the job done. So I did that. So a picture's good, and really just make sure you know what's going on here, okay? And the question asks us, how fast will the water level, water level, that's code name for H, okay? That's, the water level, is how high the water is in there. So we're going to find that out. So first of all, let's write our original equation. The volume equals 1,000 pi r squared h liters. Okay. The derivative of volume is negative 2,800. And the derivative of h, height, with respect to time, that's our unknown. So let's go back to our first equation right here. Okay, that's V equals 1. I'm going to write it again, loud and proud. And we're going to take the derivative of both sides. So we're going to take the derivative with respect to time of both sides. So what's the derivative of volume with respect to time? It was given. It's negative 2800. What's the derivative of this side of h with respect to time? Well, it's this constant. We're taking the derivative of h with respect to time, so that's going to be dh over dt times the constant. Okay, this whole thing right here is a constant. Okay, remember I told you the radius. Remember the radius, it doesn't change. As volume shrinks down, the radius still stays the same. So even though it's a letter instead of a number, we still treat it just like a real number, a constant. So what we'll do is we'll take the derivative here, and that is 1,000 pi r squared. Okay, don't be tempted to take the 2 down and take the derivative there, times dh dt. Okay, now let's divide both sides by pi r squared. That's just going to be what, 28, right? Or 2.8, sorry. And it looks like we're in liters per minute. Liters per minute. Okay? So that's what we did. Okay? So let's go back through it. Let's go back through it. We had a tank and we were draining water out of it. Okay? It had a radius r, height h, v was 1,000 pi r squared times h. That's what the volume was. And the volume changed. The derivative of this thing is 3,000. Or the derivative of volume was negative 2,800. Okay, so we knew that. So we set an equation up. And this was our equation. Okay, here was our equation. We set that up. We took the derivative of both sides with respect to time, and we found the rate at which the height changed. And I made a mistake. I put liters there. Did I even have? I'm just looking here. Okay, yeah, this didn't have anything on it. Liters per minute. So, yeah, H could have been in inches. It could have been meters. So, to be proper, we'll just say this. 28 units per minute. That's how, so roughly 3 units. So, say it was 3 units tall. After 1 minute, this tank would be empty. So, or its height would be 0. Okay? I hope that helps out, and if it didn't, don't worry. These take time. They're one of those things that just take time and practice. So, I'm going to do a lot more videos on them. So, many more to come, and there's many different ways to twist and turn this. So, we just got to get... The main thing is to just get used to writing down what you know, being able to draw a good picture, and a good picture doesn't mean, a nice, don't make a damn oil painting of the thing, but, just nice to where it's neat enough for you to know what's going on, and, all that sort of thing. Like, if you read this and drew a sphere, that would be a problem. Okay, I mean, we need to notice, all the shapes and stuff are. So, all right, more to come. Okay.